Good morning, everyone. My name is Dr. Divine Kumah, and today's lecture is going to be on thin film synthesis using a technique referred to as molecular beam epitaxy. So in my talk today, I'm going to go over how this technique works, which is referred to as the MBE technique works, and how it allows us to create new materials one atomic layer at a time. So in this technique, the way it works is that you have a molecular beam, which is formed by evaporating different elements which are really high purities inside of an ultra-high vacuum system. And by controlling this process, we're able to make atomic layers which are formed when these different materials react on a crystal surface. So before going into how this technique works, I just want to motivate why we have to grow materials one atomic layer at a time. So nature around us is fascinating at all scales. Nature has its own way of making very complex materials, and some of these we typically take for granted. So if you take an apple, for instance, an apple is large, it has dimensions on the order of centimeters and meters. And an apple has different colors, it has really good taste. But all of these come about because of the way the atoms inside of the apple are arranged. And so if you have a really powerful microscope, what you're going to see is that each piece of this apple here is made up of molecules which contain carbon, hydrogen, different metals, which are arranged in very specific ways to give apple its interesting characteristics. And so by understanding how these atomic scale arrangements lead to the properties of an apple, for instance, we can also think about making new materials from scratch where we take the elements that nature gives us, so all different elements in the periodic table, and arrange them in very specific ways to get a very specific property out. So in this periodic table here, which most of you are all familiar, or all of you are familiar with, we can arrange different elements found in nature by the number of electrons and protons and neutrons in their, which they are made up of. And if we can arrange them, for example, this table here, going across here, we get increase in atomic numbers. And each of these elements here in its pure elemental form will have some unique, distinct properties. But even though we have these pure elements, the actual properties of these materials also depend on how the atoms are structured, or the crystal structure. Right, and so if we take carbon, for instance, if you have carbon atoms arranged in this structure here, which is referred to as the diamond structure, right? The blue atoms here represent carbon atoms, but if they're arranged in this very specific pattern with the characteristic spacing of about 3.5 angstroms, this forms diamond, which is really, really hard, which is insulating, and which has all these properties derived from the fact that it has this very particular arrangement of the carbon atoms. If we take the same carbon atoms and arrange them, so we arrange the carbons as hexagons, which are weakly bonded along this direction here. We have a material which isn't as hard as diamond, but it's still made up of carbon. We have this material called graphite, which is dark. It isn't shiny like diamond. It has different optical properties and different electronic properties, just due to the way the atoms are arranged in this particular structure. Now, if we took just a sheet of this graphite, so rather than having a stack of these hexagonal planes, if we took just a single sheet or two of them and arranged them in a very particular way, this material goes from being a material, carbon goes from being a material which is insulating, expensive, shiny, when it's in this diamond structure, to a material which has some really interesting transport properties. So in this graphene case, the material becomes metallic and superconducting, and people are trying to now grow this material in a single layer form to make really interesting and cool electronic devices. All right, so going from the example of the apple, if we peer down far enough, we can see that there are atoms which are arranged in very specific ways. But by understanding how these arrangements also lead to these interesting properties, as in the case of carbon, we can now think of making new materials with interesting properties. So in doing so, we have to be able to now build materials from the ground up. And one way we can do that is, again, by this ability to grow materials one atomic layer at a time. So in this cartoon I'm showing here, I'm showing a diagram, an image here, which is a transmission electron microscope image, where a couple of different materials are grown, but they're only grown to be a few atomic layers thick. So in this picture here, there's a material called lanthanum aluminum oxide or lanthanum aluminate. Each of the bright spots you see here is an actual column of atoms. And if we go up in this direction, we are going up in what we're going to call the Z direction. So in this case, on this lanthanum aluminate substrate, we've been able to grow 1, 2, 3, 4 layers of this material called lanthanum nickelate, which is a good metal, but can change from being metallic to being insulating under certain conditions. And on top of this material, we've grown a very thin layer of another material, lead zirconia titanate, which is a ferroelectric material. So this particular combination here is grown so that we can change the polarization of this PZT, lead zirconia titanate, to change how metallic or insulating this lanthanum nickelate is. So this particular stack here is designed from the ground up so that we can make switches which are similar to the kind of basic units you find in transistors, which form the basis for computing and the storage of memory. Right, so if we can grow my material as a thin film, make the material very, very thin so that along one direction, it's only a few atomic layers thin. There are a couple of interesting things we can do. One of the things we can do is referred to as strain engineering, where we can take a material which has some crystal structure. So for example, if you took some of those layers of diamond or graphite, and you grew them in such a way that you could stretch them or compress them by tiny amounts. This is referred to as strain engineering. And strain engineering has been used to change the properties of materials significantly, because by moving the atoms in a particular crystal structure closer to each other or further apart, you can also drive very, very interesting changes in the electronic and magnetic and optical properties of these materials. Right, so one way by which you can engineer strain is by growing a material. So we can grow a material, for example, this material shown in yellow, on top of another material shown in pink. And if we can do this in a way that is epitaxial, so in epitaxial, I'm going to talk a little bit about what epitaxy is, but it effectively means that the material you're growing is going to try and mimic the pattern of the layer below. And in mimicking this pattern, it can lead to the structure of the material you're trying to grow either being stretched or being compressed. The other way, the other reason why we grow these materials as thin films is that we can form interfaces. So we can grow materials with different compositions and different properties and make stacks of them. And at these interfaces, in many, many cases, effects which are not found in the material sitting off the shelf can be produced. For example, some of these interfaces between materials which might be insulating by themselves, we can make materials which are superconducting and materials which are magnetic. Right, so the ability to make materials and grow them as really thin atomic layers allows us to use this approach of interface engineering to produce new interesting effects. Another thing we can do by growing these materials as thin films using this molecular beam epitaxy technique is that we can make what are called nanocomposites, right? So you can not just make a film, but you can pattern your material such that you can form films of different materials, which are now confined not just along the vertical direction, but in the lateral directions. And there's a really wide range of applications and effects you can create by creating epitaxial nanocomposites. Right, so if you want to create a material one atomic layer at a time, there are a couple of things are hopefully motivated so far that we need to be able to control. Right. The first thing is that we need to be able to control the chemistry. So we need to know if we want to put carbon in there or combine carbon with, so I'm using carbon as an example, but I'm going to be talking mostly about metal ions. So for example, if you have titanium, we want to combine it with lanthanum or strontium in a particular ratio. We have to be able to control the chemistry or the chemical makeup of the material that we're going to produce by forming something called a molecular beam of that material. So I'm going to talk about how these molecular beams are formed and how we can tune the compositions or the chemistries of materials to create these atomic layers with really, really precise compositions. The other thing that we like to do when we're growing a material, trying to make atomic layers of a material, is also to control the atomic arrangements of that material. And controlling the atomic arrangements is referred to as epitaxy. And going back to the slide here, if we want to control, for example, the lattice spacings of one material that we're trying to grow, then we can choose a substrate with a very well-known, well-defined arrangement and spacing of its atoms. And if we choose a right combination of these sets, then we can produce this epitaxial growth to tune the atomic arrangement of the material. The other thing we can do with epitaxy is also change the crystal orientation or the crystal structure. So in most materials, if you were to grow them out of solution or just to try and make a big ball crystal, there is some equilibrium structure, crystal structure that the atoms would like to form themselves in. But if we have a surface and we deposit that material on top, because of this process of epitaxy, where the atoms you're putting on top want to mimic the arrangement of the surface, you can also use this as a way to control the crystal structure and the crystal orientation of the film you are growing. So that is going to be referred to as epitaxy. And I'm going to break up the rest of my talk into talking about how we create these molecular beams and also how we achieve the epitaxy during the growth. So I have chosen these words here for a very specific reason. So in chemistry, we have the molecular beam, and in atomic arrangements, we have epitaxy. And if we combine all of this together, we end up with molecular beam epitaxy. So how does molecular beam epitaxy work? Before we go into the nuts and bolts, literally into the nuts and bolts about how this growth technique works, I'm just going to show you a few pictures here illustrating what most systems will look like. So if you go into an MBE lab, a molecular beam epitaxy lab, you're definitely going to see lots of steel. So what I'm showing here is one of the chambers we have in our lab, where the stainless steel chamber here has a really low pressure. So it has a really high vacuum inside. And inside of this chamber with the high vacuum is where we perform the molecular beam epitaxy process, right? So the basic components you see here are the chamber here, which is where we actually grow the material. At the bottom of this here, so in this location and that location and all around the base of this system are the tools which we actually use to form the molecular beams. So those are called effusion cells. And I'm going to talk about how those effusion cells also operate. Sticking up from the top here is something called a substrate manipulator. And so what a substrate manipulator does is it holds a single crystal substrate, so the template on which you want to grow your material. It allows you to heat up, to control the temperature of that particular crystal substrate. And controlling the temperature of the substrate allows you to control the epitaxial process when you're trying to grow a material. So even though this system by itself might look a little bit complicated with all the wires going in and out, the operation is relatively simple, and I will again talk about that in some more detail. There are other tools. You might go into an MBE lab and you might also see not just a single system, but a whole array of systems hooked up to each other. And so in a lot of cases, a lot of these other complementary systems are systems which allow you to characterize the material you're growing. So for example, the system here at Brookhaven National Lab, the MBE system itself is this system right here. But it's attached to something called an angle resolved photoelectron spectrometer, which allows you to characterize the electronic structure of your material that you've grown. This particular system here has a hole in the ground under the MBE system so that you can grow your material, transfer it down this hole in a vacuum tube, down into a microscope, a scanning tunneling microscope. And the whole point here is to allow you to grow your material and without taking it out into the atmosphere so that it doesn't get contaminated. You can perform a lot of these high resolution spectroscopy and characterization techniques. So going now to the nuts and bolts, this is the primary, the main structure of an MBE system. So in most MBE systems, you have something that holds a substrate and allows you to rotate the substrate and control the temperature of the substrate. And so this rod here is just a schematic to represent that substrate manipulator. And so going back to the picture I have here, the substrate manipulator is this whole system here, which extends into the MBE system. And it sits on bellows, which allows you to move your sample in X and Y to get it centered, but also to rotate it during the growth so that you get a uniform deposition of your thin film, right? So this whole system here allows you to rotate your substrate during the growth as you grow. So the outer part here, this is usually made up of stainless steel, and it's attached to this stainless steel are what are called vacuum pumps, and vacuum pumps suck out all the gases and all the anything that's any gas molecule or atom that's inside your material. They suck it out so that the pressure inside your system, inside this region shown in white here, is usually on the order of 10 to the minus 10 torr. So think about going into outer space where there's really nothing. And the reason why you want this nothingness is that you only want, the only material you want evaporating, the only gas molecules you want inside the material are the molecules which are coming from the elements that you like to react together to form your thin films. Right, so going back to the picture I have here, one of the pumps, this extension out here is something called a cryo pump, which allows you to maintain a really, really good vacuum inside the system. And one other component you find in most MBE systems are these valves. So this straight section here is something called a gate valve, which allows you to separate your MBE system from some external tool. So in this case, if you close this valve, that will prevent this vacuum pump from working. And on the other side here, there's also a gate valve here, which sits between the chamber in which you grow your material and a second chamber where you load your materials or remove the materials. And the point of these gate valves here are to isolate the MBE system from the environment, from the other tools, and maintain a really, really clean environment here for your growth. So at the bottom of most MBE, so in the MBE system, right, you have a substrate which forms a template on which you're going to grow your material. But what I'm showing at the bottom here are these tools called effusion cells or Knudsen cells. And these effusion cells here each contain a high purity material. Right, so the different colors here represent different high purity materials. And so you could have, for example, titanium, manganese, strontium, bismuth, for instance. And the way the system works is that you are going to heat up, in these effusion cells, which you can heat up the source materials from anywhere from a few hundreds of centigrade up to 2000 degrees centigrade. And you are going to be heating up these materials to a temperature which will cause the metal or whatever source material you have in there to evaporate and form a molecular beam. And so each of these effusion cells has a cover or a shutter. And if you close the shutter, the material does not come out. If you open up the shutter, that material comes out. And you can see in this picture here that the material coming out forms a very straight beam. And the reason it's forming a straight beam is that because your chamber is under ultra-high vacuum, there are no other gas molecules which are going to knock your material and cause it to just diffuse randomly in your chamber. So in these particular systems, you're forming a molecular beam because of the ultra-high vacuum and the fact that when you heat up the material, you give the molecules or the atoms some kinetic energy, so they start to move, and there's nothing to cause them to scatter. So they're going to form a nice straight beam all the way up to the substrate on which you want to grow. So the shutters here allow you to control the chemistry. And so if you wanted to grow materials, this blue, red, and green material together, without the yellow material, you're going to open up these shutters, allowing these materials to form the beams, which then condense on the substrate surface. So the other thing you have in most typical systems, so the manipulator allows you to rotate the substrate on the temperature on which you're growing. But these substrates also have to be heated to usually from a few hundred centigrade to really high temperatures. And the temperature of which the substrate is held depends on what material you're trying to grow and the substrate you're trying to grow it on. I'll talk a little bit about this process of why you need temperature, but the whole point is that when these molecular beams hit the surface of your substrate, they need some thermal energy to be able to diffuse on the surface to form a single flat layer, but also to react to form the crystal structure that you would like to produce. Right. So the next other main component of MBE systems is something called a beam flux monitor. So there are many ways of positions a beam flux monitor could be positioned. Some of them might not be in the position of the substrate, but in most typical systems, there is a beam flux monitor which you can slide in to the position of the substrate before the growth to measure the flux, so to measure how much of the materials you are evaporating per unit time. And being able to measure the beam fluxes and monitor them allows you to very precisely control the chemistry, the composition, and the thickness of the films that you are trying to grow. Right. And so when you're growing a material just one single atomic layer at a time, it's usually very difficult to see what you're growing with the naked eye. And if you didn't have any way of actually knowing or characterizing the materials you're growing during the growth, then you have to grow the material blindly, take it out, go do electron microscopy, X-ray diffraction, and then figure out if you actually grew what you want to grow. And if that didn't work, you have to come back and then tune the temperature, the growth rates, and so on to optimize the film growth. There are some tools which you can use in situ. So in situ means that there are tools you can use to monitor the growth while the growth is happening. And one very common technique is called RHEED, or reflection high energy electron diffraction. So I'll talk a little bit about how this technique works, but essentially you have a RHEED gun which produces an electron beam that hits the surface. And if your surface is nice and crystalline, then that is going to lead to reflection onto a screen you can pick up with the CCD camera, which allows you to map the crystal structure of the surface, just the surface, and also the smooth atomic smoothness of the surface of your the material you're trying to grow. So going back to this picture here, the RHEED comes from the other end of the backside of the system. And there's a screen here which captures the diffraction pattern, and a CCD camera connected to a computer, which allows you to monitor this diffraction pattern during the growth of your thin film. All right, so we're going to go through these different components, and I'm going to say a little bit about how some of them work. And hopefully by doing that, we can get a complete picture about how this MBE operation goes about. So the vacuum pumps, as I mentioned, are required to obtain really high vacuums in these systems. And there are different kinds of pumps which can be used depending on what kind of base pressure that you like to achieve. One common type of pump is this system here called a cryo pump. And the way a cryo pump really works, simply works, is that you have a cold finger, so a finger which is cooled down using liquid helium to a few Kelvin. And as you suck out all the gases from your chamber, they land on that cold finger and they get frozen into place, right? And so this is a basic schematic of the system. You have these charcoal-coated cryo panels. You attach this to a compressor which circulates the helium and maintains a really cold temperature here, a few Kelvin inside here. And in this port here, this is where you suck out all the gases from your material, and they come in here and they condense on the cold finger. So a cryo pump can operate as long as that surface is not saturated. And so over time, as you continue to suck out materials, they're going to accumulate on the surface of your cryo panels. And after a couple of weeks or months, depending on how often you go, you have to warm this cryo pump up and pump out everything that then evaporates and gets off from the cryo panels. And then you can go back to again pumping your main system. There are other kinds of pumps which are used. This is something called an ion pump, and this is called a turbo pump. And they all have different ways by which they operate. But the whole point of all these pumps, and in many cases, you might even see a combination of these pumps on a system, is to pump out all the gases and maintain a really, really clean system with a really high vacuum. So once you've created a vacuum in your system, and I should also point out that in most MBE systems, whenever you open them up to service them or to put in source materials, you end up with water vapor getting into the system, which has to be removed. And in many MBE systems, one thing you might see, which I don't show here, is that you're going to see a lot of aluminum foil. So there's a little bit of aluminum foil here. But whenever we open a system, we have to bake the system. So baking a system means we pass current through these resistive tapes, which causes the walls of the system to heat up to about 100 centigrade. And so we cover all of that with aluminum foil. And as we heat up the outer surface of this MBE system, the water which sticks to the inner walls comes off, forms a vapor, and gets sucked out into the cryo pumps, allowing us to get down to the really low pressures which are needed for growth. All right, so we have these pumps here which allow us to obtain these ultra low pressures. But now we like to create the molecular beam. And we use these things called effusion cells to create the molecular beams. So this is what a typical effusion cell or Newton cell looks like. This part of the system sticks into your vacuum system. And you have these things called copper gaskets, which allow you to form a really good seal between the chamber and the outside, right? So you don't want gases leaking from the outside. You want there to be a really good, nice pressure, low vacuum, clean system inside the chamber, right? And the top here is a shutter. So the shutter again opens and closes to allow the material you're evaporating to come out of to form a beam up to your substrate when you want to grow that particular element. And inside of these effusion cells, you can insert these things here called crucibles. So these crucibles are made of really high purity materials. The common ones are made up of graphite or alumina or tungsten. And you have to choose a particular material for your crucible which does not react with the material you are trying to deposit. So there's a whole science to choosing what particular material of your crucible is going to be useful depending on what material you're trying to evaporate. So I call these effusion cells, it's typically just a pan that gets heated up with some material inside. And this is the basic setup. You put in your crucible into this region in here, and there are coils around it, which allow you to heat up, resistively heat up the crucible to some temperature, which is usually very high, and we could go up to about 2000 centigrade. And inside of this crucibles, you're going to place your high purity element, which you like to deposit. And there are feed throughs on the outside here, which allow you to monitor the temperature of your evaporation temperatures, and also control the current, and which effectively controls the temperature at which that cell is. Right. So in MBE, so we have a system of the stainless steel chamber there, which has a really low base pressure. Again, I said that's in the 10 to the minus 10 torr regime. And if you want to grow any material, you have to heat up that material so that it forms a vapor with a vapor pressure which is not too high, but also not too low. It has to be higher than the base pressure so that stuff moves. But if it's too high, then that's going to make your pressure in your system no longer ultra UHV, right? And so typically in many growth systems, we need to have vapor pressures which are less than 10 to the minus 5 torr. And so these curves, these kinds of plots allow you to kind of predict what temperature you have to heat up any given material to get a vapor pressure. And the white circles indicate the melting point of those materials. So for certain materials, you can actually evaporate them with, if you're looking for a 10 to the minus 5 torr vapor pressure without them melting. So for cobalt, for instance, if you want to have a 10 to the minus 5 torr vapor pressure, you'll have to heat it up all the way up to about a little bit up 1100 centigrade, sorry, about 1200 centigrade. But to get 10 to the minus 5, you're going to be, so you can think of this as more of a sublimation process where the vapor is formed without the material melting. Some materials actually melt before you hit that pressure, that vapor, the desired vapor pressure. So aluminum, for instance, here melts a little bit below 800 centigrade. But if you're trying to get a 10 to the minus 5 torr vapor pressure, you have to heat it up close to 900 centigrade. So in this case, you can think of water boiling off to create that vapor pressure. Right. So when we are trying to grow a material, we have to create we have to choose a temperature at which it forms a particular vapor pressure, which is compatible with the MBE systems. But we also have to, depending on the complexity of the material we're trying to grow, we also have to very carefully determine the fluxes, how much of that material we are evaporating per unit time. So the way that most systems work, one particular very common way of measuring fluxes is using something called a quartz crystal monitor. And a quartz crystal monitor is usually a gold crystal, and this crystal vibrates at some frequency, so it's moving up and down, vibrating at some really high frequency, at some resonant frequency. And as you evaporate a material, as you form a beam and the atoms start to stick, that makes the gold crystal heavier. And so when you're changing the mass, that changes the frequency, causes a shift in its resonant frequency. And so by measuring this shift in the resonant frequency, you can very precisely tell how much of that material you are evaporating per unit time. So in this typical experiment, we are typically trying to get one atomic layer of any given material per minute. Right. So we will open up one of those shutters for one of the cells, carefully change the temperature until we get the desired rate, and then close that and then move on to the next material. And so once we've done all this calibration, we can now produce to actually growing the thin film. So the epitaxial growth process works this way. So if you have a substrate, so a substrate is usually some single crystal that we can buy commercially. And these substrates are typically single crystal, and they typically have to be very, very flat, so almost atomically flat on the surface. And when we put this in the chamber, we're going to heat up this substrate to some temperature. I'm going to call T substrate. And as we evaporate the molecules or the atoms of the materials we like to put on, when those atoms or molecules hit the surface, because the substrate is at some high enough temperature, those atoms or molecules will now diffuse on the surface and land in very well-defined locations, so the lowest energy locations. And so because of this temperature, this thermal energy that the substrate provides, the atoms you deposit on the surface are going to not just clump up and form islands, but are going to diffuse and form one layer, and then the next layer, and then the next layer, and then the next layer. And this growth process is referred to as the layer-by-layer epitaxial growth mode. So for this to happen, it's really important that the spacings of the lattice that the substrate has is very, very similar to the spacings of the materials that you're trying to deposit. They don't have to be the same. They can be different by a few percent, but as long as this difference isn't really, really large, you can then create these materials with really, really excellent heteroepitaxy to form. To again tune the lattice arrangements, and by stretching them or compressing them, or tuning the crystal orientations, which I alluded to at the beginning of the talk. And during the growth, the electron beam allows you to monitor the surface crystal symmetry. So the RHEED gun here, so that produces an electron beam that hits the surface and gets diffracted. And this is a real kind of image we can get from a CCD camera from the surface of a material we are trying to grow. So these really bright peaks here are because of the two-dimensional symmetry of the surface. And if we take one of these peaks here and we monitor this intensity inside of this here as a function of time, one thing you'll notice if you have layer-by-layer growth is that this intensity oscillates as a function of time. So when you're starting to grow your material, the surface is nice and smooth. So you end up with really, really strong specular reflection. And as you start to form, as the layer starts to form, it starts off with these small islands which form in different parts of your material, atomically high islands. And that causes an effective roughness of your surface. So when you get about halfway, get to about halfway coverage, it's almost like you're trying to reflect light off of a very rough mirror. That leads to a really low intensity. And the intensity comes back up when you form a complete layer. So using this technique, every oscillation here corresponds to the growth of a single atomic layer of the material. And we can very precisely monitor the growth, layer by layer growth, using this in-situ electron diffraction technique. The spacings of these atoms here also tell us exactly. So if I measure the spacing here between these peaks here, it's inversely proportional to the spacings of the atomic layers on my surface. So using this electron diffraction technique, I can also tell during the growth the spacings of my atoms and the kind of symmetry they have. And it also allows me to control things like the substrate temperature, the growth rates to get the right atomic spacings and atomic symmetries which are desired. So once we've gone through this whole process and achieved this molecular beam, this epitaxial growth, we can now create materials which do not exist naturally. So this picture here is a transmission electron microscope image, which is taken after we've drawn the material, where we've here tried to grow a few layers of this material, which contains chromium, spaced by another layer of this material, which contains manganese. And this high-angle annular dark field image here tells us that the atoms are arranged in nice straight columns. There's a really sharp interface where it goes from this brighter region to the dark region where the film sits related to the substrate. But we can use other techniques in an electron microscope to give us more information about the chemistry, to again go back and do a post-analysis of the chemical purity of the layers that we've tried to grow. And in this case, using this technique here, we can precisely tell that the regions between these chromium layers definitely have more manganese, which is what we aimed for when we grew this material. Right, and so in this case here, we're trying to grow these chromium manganese layers to control the magnetic properties of these systems and grow them on a substrate. And the substrate we grew on a strontium titanate. And strontium titanate allowed us to compress to stretch these films a little bit, tiny bits to change the magnetic properties of this particular multi-layer film. All right, so we can grow these materials, we can characterize them whilst we're growing them, and those are some of the advantages of the MBE technique because it's a very slow process. It allows you to use some of these really complex tools to monitor the growth process. It allows you to also get really high purity and materials with really sharp atomically abrupt interfaces. And we're also doing experiments at other facilities, for example, at the Advanced Photon Source, where we can actually, during the growth, also use X-rays to monitor the three-dimensional structures of these films we're trying to grow, which we do not get when we use the electron diffraction process, right? So this MBE technique, again, it's a really slow process, but there are many things you can tune to create materials which do not exist in nature. And there's a lot to learn using a wide range of complementary tools to study these materials during the growth. And so that is a summary of my talk. If you have any questions, please feel free to send me an email at divine.kumah@duke.edu. Thank you very much.